Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 16th lecture on the course Maritime Structures under Fire, Blast and Explosion, offered on the SwayamPrabha portal at IIT Gandhinagar. In lecture number 16, we are going to learn now today how to estimate fire loads. In the previous set of lectures, we have been understanding the consequences of fire, difference between fire, explosion and blast, different models which will help us to understand fire classification and explosion consequences. We have also learned how to mitigate the consequences of fire and explosion using flammability diagrams, emergency response planning guidelines, etc. So now fundamentally when you move into the structural fire engineering, we need to do the calculations to check and design the structural system for fire safety. Friends, designing a structural system for fire proof is practically impossible, but we can always make a structure to resist fire for certain duration. We call this technically as fire rating. Fire rating is that time expressed in minutes or sometimes in hours of any structural system or a component of a structural system which confirms that the structure will remain structurally integral, may not be functional, structurally integral without collapse for that duration under a specific class of fire. For example, if I say the structural fire rating for 500 degrees Celsius standard fire is 30 minutes, if the same structure is exposed to a hydrocarbon fire of high temperature of 1200 degrees Celsius, the fire rating will be now different. So, fire rating also depends on the classification of fire for which it is rated. So, generally for maritime structures, we have to first define the classification of fire, probability of fire occurrence before we enter into fire rating or doing fire resistant design. In fire resistant design part, it is essential that we first understand how to compute fire loads. We know how to compute structural loads such as dead load, live load, impact load, ice load, earthquake load, etc. But it is a new concept at this moment for us to learn how to compute fire loads. We have learned from fire engineering or fire chemistry how fire formulates, how fire spreads, how it is classified, what are the vulnerabilities and what are the factors which governs the fire growth and so on. Gradually, we must convert our learning and understanding to a process of mathematics to compute the loads for which structure must be designed. So, let us look back this particular slide which we emphasize again. One of the serious consequences of fire is expressed in this slide in a very brief form. Any design methodology will always have a capacity and demand. Let us say this is the demand and we have a target capacity. We always design the system in such a manner that the capacity exceeds the demand and there is a difference of what we address as margin of safety in the design. But when the system is under fire, this margin of safety is compromised because system under fire will also invoke additional thermal stresses where the stress level will get increased to a certain extent. Furthermore, the strength of the material will also get degraded as the temperature increases, which we already learned from the previous lectures. Therefore, friends, the margin of safety what we see in the design is now compromised and get narrowed. There is a possibility that the thermal stresses may even overlap and you may get zero margin of safety as well. So, one has got to be very clear and confident in estimating the structural design carefully under fire. So, fire resistant design or fire structural engineering is a complicated task, but a very mathematically laid procedure. So, we will slowly get into this business and understand this with application examples to concrete and steel structural members slowly with design examples. So, you will learn them, but on the other hand, to reinforce your self learning, please have a look to these two books, Fire Resistant Design of Structures by myself and Gaurav for CRC, Design Aids of Offshore Structures under Special Environmental Loads including Fire Resistance by Springer, written by me and Gaurav. So, please have a copy of these books in your library for your continuous reference and reinforced learning, as well as refer to these as standard material for this lecture. Friends, if you want to compute fire as structural load, let us see what are the steps involved in doing that. To compute the fire load, I must first calculate the total amount of combustible item present in that space. Every material or every element present inside the space will also have something called combustible property, and I must compute that combustible property number and its combustible amount in terms of joule or megajoule and that becomes my fire load. And when the fire load is estimated, we should also have an idea about the behavior of fire with time. This can be done using heat release rate or time temperature fire curves. Once we learn this, then we compute the structural temperatures through heat transfer calculations within the structural members, and then we land up in computing fire ratings, which will help me to compute how long the structure can withstand engulfing fire. So, fire as a structural load is a process involving 4 different steps. At the final step, we land up in calculating fire rating. Let us see now one by one. If you want to compute fire loads, maybe in a building or on a maritime structural system, etc., let us ask series of questions. What is a fire load? Anything that can burn releases fire load. How is it characterized? It is measured in energy units. It may be either in joules or in calories. It is characterized as energy per unit area, that is joules per square meter. Once I do this characterization, I call this as fire load energy density, which is called FLED. What does it represent? The total amount of available energy that can be released in an event of fire is an indicator of FLED. FLED tells me what is the total amount available when a fire is set, which can be further released. What are 2 important considerations in estimating a fire load? The amount causing the fire load, then most importantly the geometry layout of the rooms, opening sizes, locations, etc. Now, the second part is a very important aspect in maritime engineering, because in maritime structures the geometric layout, the machinery layout and the equipment layout are not completely controlled by the maritime designer. It is all controlled by the user defined inputs. For example, the electromechanical equipment layout does not and cannot be dictated by the fire load estimates. It has got to be decided by the process layout. So, once the layout is completed for process requirements, the maritime engineer has to check what is the vulnerability of that layout in terms of fire load. So, it is actually a reverse calculation. But in a building which you want to plan in advance, you can estimate and locate the vertical and horizontal zoning of these spaces according to fire safety regulations. Let us now try to get into the physical sense of what we talk about energy. If you say joule, a 50 kg human walking very slowly, maybe at a speed of about 0.2 meter per second or about 0.75 kilometer per hour. 1 kilojoule is actually 1 cup rice, which has got about 284 kilojoules. 1 megajoule, of course, is 1 kilowatt hour of electricity, is about 3.6 megajoules. If you burn wood of 1 kg, it releases about 17 megajoules. These are all physical numbers which will help us to learn a physical feeling of these numbers. Gigajoule can be also understood as 1 barrel of petroleum releases about 6 gigajoules. 1 barrel means about 160 liters. Terajoule, 63 terajoule energy was released by the little boy, which is actually the space element fired in the body. Let us now compute the fire load and fire load energy density. Fire load of a room can be computed using the following equation. It is algebraic sum of the mass of combustible item and the product of that with its calorific value. Every combustible item has a respective calorific value which can be expressed in joules per kg. So, if I say I have a matter or substance whose caloric value is 2 joules per kg, and if I know how many elements of that order in terms of mass, let us say 3 kg, I can now say this mass, if it burns completely, will give me 6 joules. So, I am trying to compute the energy release in joules, kilojoules or megajoules based upon the product of sum of mass of the combustible item and the calorific value of that item. The calorific value of almost all items are available in the standard steel or design tables. So, if you do not have a standard table which gives me the calorific value, one can also conduct a survey and conduct experiments in fire laboratory to find out the calorific value and then use it. So, this is very useful to be determined for new materials. FLED then is that fire load divided by area. The moment I say area, it is the area of the floor. Sometimes it can be also internal surface area total. For example, if I have a room, so let us say L, B and H. Usually FLED is energy divided by this floor area. So, usually FLED is the total energy which you compute from here divided by L into B. You can also compute FLED based on the energy divided by total internal surface area, which means you have to add the area of these walls along with the floor, and you can delete the ceiling. In this, you can also exclude any opening of windows and doors. So, one can say total internal surface area. Okay, both are FLED. So, FLED will be now expressed in units of megajoules per square meter. Then I can compute this in terms of something called heat release rate, which will be this energy released by time, that is so many joules per second. So, now I will convert the energy release into heat units. That is what we do here. Joules per second is watts, can be kilowatt, megawatt, etc. So, I can now compute small capital Q, which is HRR, we call it as heat release rate. If we then divide this by area, then I will get heat flux, which is watts per square meter. So, this is expressed as small q. So, small q is related to FLED, capital Q is related to E. Okay. So, these are very common terms which is repeatedly used in structural fire engineering. Just for knowledge sake, let us see some materials listed in the table and the corresponding calorific value which you can see in the table here. If you look at, for example, charcoal, the calorific value is 28.4 into 10 power 3 kilojoules per kg. Okay. So, essentially it is megajoules per kg. So, so if you know how much quantity of charcoal is present, multiply that with the mass of the charcoal, you get so much of megajoules. Similarly, if you look for gas oil, look for propane and even common solids like rubber, most of these are covered in all are flammable material. You can see, for example, flux, bitumen, asphalt, rubber, pitch, wax, even bread, even flour, cornmeal, all are actually combustible. If you are able to compute the total mass present in a specific space, correspondingly the calorific value is known, one can compute what we call as the energy release during fire, if it sets to fire. I want to also draw your attention to one more class or column of this table, the last column, which is wood equivalent. For every fuel, be it solid fuel, hydrocarbon, foodstuffs or common solids, there is also an equivalent given in terms of wood. For example, anthracite of m kg of mass, whose calorific value is 28.6 megajoules per kg, produces the same energy as that of m mass of wood, whose calorific value or the equivalent is 1.66. So, I will convert all these into equivalent wood. So, if you recollect, we did the same thing in terms of explosion calculation for TNT. We did the same process for TNT. We converted all explosions in the form of TNT and found out equivalent TNT before we compute the damage from explosions. A similar exercise is also recommended in fire engineering, that I convert all the burnable or flammable material into equivalent wood. So, for all flammable material, equivalency is also given in the same table. Okay. So, calorific value of common materials can also be seen in standard tables. The table is extracted from National Building Code Part 4, Indian Standard Code of Practice, Table 9. Let us see quickly an example. Let us say I have a storage room of space containing 100 kg of cellulosic material. We want to compute the average HRR during fire accident, which lasted for 45 minutes. So, what I do? I compute first the energy. I have the mass of the cellulose. I must now compute and convert this into equivalent value of, let us say the calorific value of cellulose is 17.6. So, I get the total energy. I divide this energy in terms of time. So, I am saying the heat is lasted for 45 minutes. I convert that into seconds. So, megajoule per second, I get so many kilowatts. I am converting energy into heat units. Okay. If I divide this further by area, I get this as flux. Okay. Let us do another example. I have a storage room which has got 10 kg of wood. The calorific value is also given. 50 kg of gasoline, calorific value is known to me. 60 kg of diesel, calorific value is known to me. What we wanted to know is the total energy that can be released during fire from this compartment, and also what will be the average HRR if the fire lasts for 30 minutes after an accident. So, first step is to compute the capital E, the energy. So, what we do? We take the sum of mass and C of all of them, find so many joules. Then the fire is going to last for 30 minutes, I divide it in seconds and I get the heat unit. So, it is very simple that even if you have one element or multiple elements in a given space, you can always compute the E value and this, where E is known the fire load and Q is known HRR. Okay. So, this is expressed in terms of heat units, this is expressed in terms of joules, energy unit. Okay. So, for a single room having multiple elements being stocked whose calorific value is known, can compute this. Furthermore, friends, we want to then characterize fire. I can do this in two ways. One, using time temperature curve, other is time HRR curve. FLED calculations, that is fire load energy density calculations, help in quantifying the HRR, heat release rate. Let us now look at this curve, HRR model for fire. Let us say if you look at the fire growth from this curve, there are different stages of fire growth. It grows from time t naught, it goes to the peak of heat release rate, it sustains in the peak for some time, then decays. So, we can very well divide this into 3 zones. This is what we call as the growth phase, sustained burning phase and decay phase. Okay? So, sustained burning phase essentially has the same HRR maintained during the entire period. If I say this Q is actually given as alpha G T square, which is about 1000 megawatts, for a specific rate of fire growth, if it is slow, medium, fast and ultra fast, this alpha G is suggested by the literature. Okay? So, I can always what would be the time is also suggested by the literature in terms of seconds. So, I can always find, I can always plot for a different rate of fire which is slow, medium, fast or ultra fast, can always compute the fire rate in terms of its growth, sustain and decay phase. Look at this consortium of figures available here. Let us say I have a unit or a box or a building. Let us say I have set fire to one corner and T equals T naught, which is here. Okay, that is an initiation of fire. Fire started. So, now the fire grows, since it started, it is growing. So, the temperature at any point here will be between T naught and Tp. This is Tp. Okay, this is the Tp. So, when it reaches sustained phase, it starts spreading on the sides. So, T will now become Tp. So, at this point, it has fully grown and fire is now sustaining. When it sustains and grows, then the temperature at any instant will be between Tp and Td. Okay, that is the temperature. After which fire starts decaying. If it is fuel controlled fire, fuel does not exist, therefore, it diminishes and decays. In the decay phase, T will be anywhere between Td and Tn, and at the end of combustion, it reaches Tn. So, it is a simple graphical representation of the same figure which is written here. So, fire has got essentially 3 phases: growth phase, sustained burning phase and decay phase, expressed in terms of time, temperature or HRR. Okay, that is a very standard HRR model which is used in structural fire engineering. Let us try to use this model and compute certain calculations. Let us say I have an office room which is approximately having 200 kg of furniture, calorific value is known and a medium T square fire takes place. Even the fire model is given as a medium fire with a peak HRR of 9 megawatts. The peak HRR is 9 megawatts. Estimate the total time of burning. How long this furniture would burn. Okay. Now, let us first compute the total energy. So, how do we do that? I take the mass, multiply with the calorific value, get the energy. This 17 megajoules with 200, I get 3400 megajoules. Now, I want to find the growth rate factor for medium fire. Let us go back to this table. For a medium fire, the growth rate factor alpha G is 0.0117 kilowatts per second square. So, I say 0.0117 kilowatt per second square. Let us now try to find out how much time it takes to reach the HRR peak. So, that is going to be alpha G T square. Okay. Therefore, from this I can compute Tp, which is I can compute Tp, the time taken to reach Q peak is computed using this equation, because I will simply say it is going to be Qp by alpha G. So, I will get 877 seconds. So, about 880 seconds the fire will reach its peak. Now, when it reaches the peak, the total energy released in the growth phase is 1/3 of this. Why 1/3 of this? Because this is actually considered as a triangle. So, the energy released is 1/3, half base height, okay, 1/3 of this. So, I compute that. So, 2631 megajoule has been released when it reaches QP, that is the HR. Now, the QP which expected to burn is about 9 megawatts. So, I have reached only, so I want to find out how long the fire will sustain to burn, that is I want to find TB, I want to find the sustained period of burning TB. So, to do that I compute TB as TP, the growth time, plus the difference of these two divided by QP. QP I already computed. Okay. So, 877 is this plus 85.4. Okay. QP is already known to me, I can compute this, and 16 minutes the fire will sustain to burn after it reaches Q peak. Okay. So, I can find using the HRR model how the burning time and the initial time to reach QP can be computed using alpha G T square model. That is a standard HRR model being used for structural fire engineering. Having said this, let us now look at the features or characterization of the time temperature curve. Okay. So, now if you look at the curves drawn on the screen at this moment, there are two curves available here. One is the natural fire curve, the other one is the standard fire curve. One first observation what we have is the backbone, the decay stage of the standard fire curve is missing, is not there. Okay? Whereas, for the natural fire curve, the decay stage or the backbone stage is available. Secondly, the standard fire curve starts after initial ignition and smoldering time, which is about 20 minutes, whereas natural fire curve starts from 0. Okay. So, it is this curve friends which is being used for structural design. Okay. Now, let us see what happens during this stage. So, this stage is called pre-flashover. The temperature will likely be less than 600 degrees Celsius. After the stage is reached, then this is called post-flashover, where the temperature can exceed even 800 degrees Celsius. So, during this time, within 600 degrees Celsius time or temperature, one can look for fire alarms, sprinklers, extinguishers, making calls for emergency service stations, fire stations, evacuation planning, compartmentation and firefighting. All has to happen only during this stage. So, friends, structural fire engineering, where the system has been designed and characterized for fire loading, is always starting after this period. See, it will start from here. So, all these are in place and then the fire loading starts actually. Okay. So, we call this as structural fire safety part. So, this is fire protection part or fire fighting part. Structural fire safety starts from this part after ignition and smoldering stage. So, this is the growth stage and this is the burning stage, and of course, the decay stage is missing in the standard fire curve. So, once the fire extinguishes, then we start doing the decay stage, then we look into forensics of post fire scenario and try to check how the devastating effects have been reported during the fire accident. So, this is a very interesting time temperature curve which gives me an understanding of what are the activities that has to take place during pre-flashover and what is the likelihood of the time and the temperature during the pre-flashover, and the post-flashover one can go from 20 minutes to 240 minutes. Okay. This is a longer period where it stays and grows or sustainedly burns. Then of course, it decays because fuel get exhausted or fuel completely get combust. But if it is not so, when the fuel is continuously supplied, then it will continue to burn, and that is the assumption what we make in the standard fire curve. The standard fire curve does not have the backbone decay stage, and remember that the structural fire safety starts only from this stage and not from here. Okay. This is what we call as firefighting or fire protection systems. Structural fire safety does not start from 0, but after initial smoldering stage. In approximately, one can say, friends, the structural fire safety is invoked only after about 500 degrees Celsius is reached. We will always check, inspect at 500 degree what is the status of the building. Okay. Let us say if I have a compartment which is ventilation controlled and I am looking for a flashover within a compartment, let us say what are the important aspects which govern this. Flashover takes place if all of the following are fulfilled in a compartment fire. Compartment is an enclosed fire. Sufficient amount of fuel is available, oxygen is available in abundance, and compartment is able to trap the hot gases. That is, there are no mechanical ventilations available on the top to release these gases, and geometry of the compartment is capable of enabling radiative heat transfer. Okay, that is very important. So, the geometry, absence of ventilators, oxygen presence, and of course, the amount of fuel. If they are all available, flashover takes place in a compartment. Thomas flashover critical heat flux for a room with a single window is given by this equation, okay, which accounts for these parameters. One can say the AT, the total surface area of the room. AV is the area of the window opening alone, and HV is height of the window opening alone. So, this gives me the heat flux at flashover by this equation. These parameters of numbers or parametric variations which are based upon experiments conducted by Thomas flashover test, and these values are taken directly from the experimenter, and therefore, this is empirical equation which helps me to compute the critical heat flux of a flashover in a compartment fire. Let us say I have a compartment of size 4 meter by 3 meter in plan and height is about 3 meter, which has got only one window of 0.8 meter by 1.5 meter. Okay. So, we will recall the earlier example where the fire lasted for 16 minutes, that is 9 megawatt peak HRR. I think we did that example here, 16 minutes where the HRR is about 9 megawatts. We calculated this. Okay. I will borrow the same example and take it forward now. So, let us say I have 16 minutes fire lasting, which is now going to take the heat release as 9 megawatt peak HRR. Say the fire happens in shown compartment, will there be any flashover? Because flashover is one part which propagates fire in a very dangerous situation. Let us check this. The compartment size is given, window size is known, therefore, I can compute the area of ventilation which is the product of these two. Okay, that is the area of ventilation. Okay. I computed this. Total area is the surface area, that is the surface area of the floor and ceiling, surface area of two vertical walls and two horizontal walls, total surface area. Okay. I compute this. So, essentially is going to be twice of 4 into 3 plus 4 into 3 plus 3 into 4 and so on. Okay. So, I can compute this. Now, once I know this, I can compute the flashover using the previous equation of this. I know the total area, I know the area of ventilation, I know the height of ventilation. Using Thomas flashover critical, I can compute heat flux Q flashover, and I am doing that here. Okay, I am doing that here. So, I have computed, these are constants, this is the area total, this is the area of ventilation, and this is the height of ventilation which I am using it here. I compute this. Now, I realize that this Q flashover is much lesser than the peak HRR. Okay. Therefore, the compartment will experience a flashover. Now, let us compute the growth rate of this fire. Assuming a medium fire, alpha g is taken from the table which I showed you earlier. Alpha g for a medium rate is shown from here. I will use this 0.0117 alpha g kilowatt per second square and use it in this model here. I will use that alpha g here. Then I compute the time for flashover using this equation and 280 seconds. So, what is required here is to compute the time flashover. Will flashover happens? If it happens, how long? So, the flashover will take place for about 280 seconds. Okay. So, these are simple calculations of fire load intensity on any given compartment fire or any given space. As you see them, proceed forward. Now, let us compute the relationship between the fire load energy density and time temperature curve. Okay. Fire load energy density and time temperature curve are based on certain experiments conducted at different researchers in different parts of the world. So, they use empirical relationships to provide details about these two curves. There are also Swedish fire curves which help us to give advanced input parameters related to time temperature curve. One can also use fire dynamic simulator to add furthermore parameters like area of ventilation, rate of escape of fire, etc. And of course, Eurocodes also use parametric curves to help us to do this. Therefore, since we have got 4 different approaches to express the time temperature component or FLED component of fire, standardization becomes an issue. So, therefore, we use something called standard fire curve. Standard fire curve is as per ISO 834 and IS 3809, which says this is my expression for standard fire curve. So, all fire ratings on any structural system are then and now onwards derived based on the standard fire curve. Because if you derive fire rating based upon any of these equations, then it may vary. Therefore, there is no standardization possible of fire rating. Therefore, fire rating is expressed only based upon a standard fire curve, and standard fire curve is given by this equation. Okay. Time versus temperature, that is what we are looking at, time versus temperature and so on, time versus temperature. So, all fire ratings must be derived based upon the standard fire curve. Having said this, let us say what is the guidance we have from the National Building Code of India. So, National Building Code part 4 table 26 is extracted here for the user benefit. For different types of buildings like residential, classification A1, A2, institutional, educational, assembly hall, mercantile, industrial and storage hazards, fire load energy density expressed as wood equivalent is given here. So, this is where we discussed about wood equivalency available in standard tables for computing fire load energy density. So, National Building Code India also gives you fire load energy density in terms of wood equivalence, so many kg per square meter. So, 25 kg per square meter wood equivalent is about calorific value is about what we look at for residential building. So, if you look at the calorific value of wood, it is about 17.6 megajoules per kg. It means I am looking at a load of 425 megajoules per square meter. That is my FLED as guided by National Building Code of India. Okay. As you go forward to commercial buildings, industrial buildings and hazardous storage yards like offshore platforms, even LNG bottling units, CNG units, etc., in port and harbors, etc., they are very high, okay, compared to this. Okay. Having said this, let us also see how the fire characterization is derived based upon the fire load estimate. So, fire load estimate, what we do is we find the mass of the element present in the system, we multiply that with the calorific value, then we compute HRR that should help me to characterize fire. So, simple estimate, energy can be computed, calorific value can be also computed for new material using bomb calorimeter. One can directly assess HRR, or one can also use something called cone calorimeter to assess HRR. So, therefore, friends, heat release rate becomes an input to the heat equation. So, heat flux, we already know that it is HRR per unit area. Okay. So, fire for design is characterized as heat release rate or flux. So, we have converted the energy unit into heat units for design. Okay. So, there are certain steps involved in fire load estimate in any given building if you want to do a survey to compute the fire loads. First step is identify the building, classify the occupancy, and catalog all the combustible items present in the building with different materials, then assess them by weight and also find the calorific value of each material. If not available, conduct experiments to compute the calorific value. Step 2, if you have got any new inventory material, collect the sample and take to the laboratory and find out the C value. The third step is to characterize this. You can do thermogravimetry analysis, cone calorimetry to compute HRR, or you can also directly compute HRR for a given building of occupancy levels. Okay. Thermal conductivity, specific heat capacity are all required to compute this characterization. So, cone calorimeter is a typical equipment being used for computing HRR. We have this facility in our laboratory at IIT Gandhinagar. So, you become part of this program of Masters and PhD in Maritime Engineering. We will try to take you and make you conduct experiments using this equipment's advanced level, and one can find out even the calorific value of different materials which are innovatively used in offshore structures and maritime industries, so that we can accurately compute the heat flux and the heat release rate for designing or assessing the fire rating of structures. We did one simple experiment recently which I am showing you the result. So, one can very well see that the wool is packed in an aluminum box and set to fire. Okay. The aluminum box or the core LDP which gets the HRR, as you see here, is decays in 400, whereas the ACP will try to not receive the heat, but starts getting the temperature rise only after certain time, up to which this withstands fire. So, if you have got any innovative, let us say package materials which are used for, let us say, acoustic proof or false sealing, or even buoyancy materials which are used in floating structures, one can also estimate those novel materials in the laboratory and try to compute the HRR versus time curve plotted for these kind of composite materials. Not necessarily they should be standard material, even if you have got any new innovative material, one can also compute HRR versus time using our experiments facilities available at Maritime Engineering Laboratory at IIT Gandhinagar. So, friends, let us look at the summary what we learned in this lecture. So, in this lecture we understood how to compute fire load, which essentially is summation of mass of any element present multiplied by the calorific value of that element. So, once I know the fire load, I can compute this is the energy. Then once I compute the energy, I can also compute HRR. I can also compute the heat flux. So, ultimately what we do in design is compute or convert the energy units of release of fire into heat units. And fire is also then used alpha g t square model for time temperature curve, and it is categorized as slow, medium, rapid and ultra rapid fire growth, for which alpha g is defined. And for different materials available in the literature, one can also see the calorific value and the wood equivalence of all of them. National Building Code of India 1984 and further revisions also help us to compute the equivalent wood HRR or flux, which is recommended for design for various types of buildings, which we learned in this lecture. So, for new innovative materials, we can also conduct experiments using cone calorimeter and plot HRR versus time curves for new materials, okay, using experiments. So, we have learned all these things in this specific lecture. We will take you forward to do more structural fire engineering in detail in the coming lectures. Thank you very much. Namaste.